So welcome back. So I'm now pleased to introduce Professor Alan Fearn, who's going to be presenting on his joint work with Professor Tom Diederich. Alan Fearn is the professor and the associate head of research at the School of Electrical Engineering and Computer Science at Oregon State University. His research is very much on automated planning, feedback, and reinforcement learning systems. Tom Diederich is the distinguished professor and the director of intelligent systems at the School of Electrical Engineering and Computer Science at Oregon State University, and just completed his term as the president of the Association for the Advancement of Artificial Intelligence. And his research is at the intersection of machine learning, data science, and big data. I'm very pleased to introduce their joint work on anomaly detection and confidence in modeling the environment for artificial intelligence. So please join me in welcoming Professor Alan Fearn.
So originally we had thought of just talking about our FLI project, and that's actually a little more aligned with robustness than transparency. But we figured out that we can try to address this topic of transparency here. And there's going to be two parts to this. Basically, we're interested in recognizing uncertainty, getting systems that can recognize their uncertainty and then explain the uncertainty. So they say goal one, we'd like uncertainty-aware ML systems. Now, this is there was a nice paper in ICML 2008. They introduced a framework of knows what it knows. And they wanted it was sort of a pack learning framework where the system had to make confident predictions. It was allowed to abstain, and they were trying to minimize the amount of abstaining while guaranteeing that the predictions were confident. So I thought that was a neat framework, and that's along the lines that we're thinking here as well. So we're going to allow ambiguous responses from the system as long as they're correct in some way that we'll specify. And we're particularly interested in studying this both in closed worlds. So this is sometimes called the known unknowns situation, where you sort of quantify the possibilities, and there's uncertainty over those possibilities. And then we're really interested in the open worlds case, the unknown unknowns case. So we don't even know all of the possibilities. So we want to explore uncertainty-aware systems in both of these cases, and why? I think there's obvious reasons. We'd like safe and trustworthy AI. I don't have to really talk about that much. I think end-user acceptability is another major reason. If the system is making lots of crazy predictions, the end user is just going to get very unclear about whether they should trust this system in any particular situation. And in my own research, this might not be an obvious reason, but computational efficiency. If you think about trying to get more and more accurate systems that have confidence, you might have to develop very complicated models. But if you can get smaller models that actually understand their uncertainty, then when they are certain, you can just go with those, and otherwise you back off to more complicated models. I study learning and planning, so I think of this in the context of, well, we'd really like to. There are a lot of obvious bad things to do, and we can be confident that they're bad. And we'd like the planning systems to sort of planning or reasoning systems to search the rest of the space. So that's another reason that uncertainty-aware AI is interesting. So goal two is transparent uncertainty in ML systems. So we'd like the systems to explain their uncertainty, not just abstain from making a prediction, but give us some insight into why they're uncertain. And this really hasn't been studied a whole lot. Again, we'd like to do this in closed worlds and open worlds. And why? Well, a lot of times I think it could be a basis for feedback to a machine learning system. I can't tell whether this is a cat or a dog because blah, and maybe you could give a piece of advice or give a new feature or say, well, this is actually a really ambiguous situation. You're right to be uncertain here. So that might be one reason you would like to explain uncertainty. At the second part of this talk, I'll talk about anomaly detection and how often explaining uncertainty can be important to the end user to give insight into the system itself. This I think even outside of anomaly detection, getting some insight into why a system is uncertain might help you debug it or improve it in some way. And then I think it's also a mechanism for building trust. If you get explanations for when a system is uncertain, and it's generally uncertain in reasonable ways, the reasons are reasonable, I think you would tend to trust a system more that has that property as opposed to its explanations are kind of crazy, and you can clearly see it doesn't understand what's going on by its explanations of uncertainty. So those are the two goals that I want to address. And the talk today, I'm going to have two parts. Part one is going to address the uncertainty awareness aspect. And we're going to talk about, it's part tutorial and a little bit of work. We're just getting started on this. But we're going to talk about conformal prediction as a way of getting uncertainty awareness, at least in the classification setting. And we'll talk about open worlds and closed worlds, some experiments there. And at the end of the day, what we're going to see is that when it comes to open worlds, empirically, and the theory says nothing, conformal prediction theory says nothing about open worlds, but empirically we see that conformal prediction is not adequate. And it suggests integrating with anomaly detection. So the second part is going to be some work we've done, more of a case study in explanations for anomaly detection. This was in a security setting. And that case study forced us to try to give some initial answers in that context to these questions. What is an explanation for an anomaly? How do you compute an explanation? And then how do you evaluate explanations? We had to try to think about those questions in that context. So that'll be a little case study focused on those questions. So first, you're all familiar. So these examples are a little cartoonish. My student picked these out. I guess it's Lilo and Stitch. I'm just going to go with them. But classification, we've got our known classes. This is if we're in a closed world. There are humans, animals, and hybrids. And a standard predictor will output one of those choices. This is a human. And this is actually a hybrid, but the system says human. We don't get much information from a pure predictor like this that would let us gauge the certainty. Some systems do give you numbers that, a larger number means maybe that it's more certain, smaller number is less certain. I find a lot of times those numbers are not very reliable. But the uncertainty is not made explicit, and there's really no guarantee from a standard predictor. Now, what conformal predictors are going to do, and this is Vovk. Actually, there was an ICML paper in 1999 that kind of set the stage for this work. He has a nice book on this type of material. Came out in 2005. But what conformal prediction is going to allow is to output sets of classes. So I'm going to focus on just the classification problem. You can also do this for regression, and then you would have confidence intervals. So we could output animal or hybrid, and we're going to say that this is a correct response if the true label is in the set. Okay? So that's fairly straightforward. Here, the system was very confident in human, and it output this set as sort of the ideal thing we'd like from a predictor. There's no ambiguity in its output. Here, apparently the system was very uncertain and really couldn't tell us anything about this object that it's looking at. So basically, conformal prediction lets us output sets as opposed to point predictions, and the correctness is judged by whether the true label is in the set. Now, you could say that this is already a type of explanation of uncertainty, in the sense that if you go back to the knows what it knows framework that I pointed out earlier by Li-Hong Li, Michael Littman's group, they were allowed to abstain or give a prediction, and abstaining doesn't tell you much other than the system doesn't really have confidence right now. This at least gives you some indication of the level of confidence in the system. And here it's kind of a reasonable. You can see these are reasonable sets in terms of understanding the uncertainty. Now, so how do we evaluate a conformal predictor? Well, one way is accuracy, right? And so conformal predictors will take as input an accuracy constraint, where 95% would mean that 95% of these sets that you output have to have the correct label in them. Okay, so that's all we mean by accuracy. And the obvious thing here, though, is that you can always get 100% accuracy by just returning all of the labels, right? So just maximizing the set size is a perfect solution if we only care about accuracy. Now, obviously, we care about more than just accuracy in this setting. What we'd like to do is remove as much ambiguity in the predictions as possible. Okay, and there wasn't really a clear measure of ambiguity in the conformal prediction literature. They would sort of talk about the number of labels. That's a hard thing to think about when you have data sets with different numbers of labels to just look at graphs. So we've introduced, for our own purposes, a notion of ambiguity that, this is the formula, that's 0 when it outputs one label. So it's 0 ambiguity. And if it outputs all the labels, it's 1. Okay? And so we see this prediction has an ambiguity of 0. This prediction has an ambiguity of 1. This is in the middle. All right? So we're going to be interested in minimizing the expected ambiguity given a constraint on the accuracy. Okay? So you'll specify a 95% accuracy constraint, and you'd like the predictions to be as unambiguous as possible. Right? And that's really what conformal prediction is trying to get at. So let's go inside. I don't know how many people have come across conformal prediction. It's not sort of a widely known framework. So I'll give you a little insight into what these systems do. So a conformal prediction system is really a wrapper around a standard learner. You can pick your favorite learner, random forest, neural network, nearest neighbor. You got your favorite predictor here. And you've got some training data. And what we're going to expect from the system is we have to be able to compute nonconformity scores from its output. And I'll show you some examples of what nonconformity scores will look like. But this is just showing you, a 6 means that it does not think this is a human because we're calling it a nonconformity score. Larger values mean that it's less consistent with this human label in this case. So we're going to assume that we can get these nonconformity scores, and actually these can be arbitrary scores. The conformal predictor will still achieve the accuracy constraint. We're going to feed those into a conformal prediction framework with an accuracy constraint, and it will output some labels. Okay. Now, the main thing that's going to control efficiency. So the conformal prediction framework, under some assumptions, the data has to be exchangeable, and there has to be some assumptions about the nonconformity score, some pretty weak ones. It will always maintain this accuracy constraint. No matter what, you could just have a pretty dumb, you could have a constant predictor here, and it will always maintain the accuracy constraint. And I'll show you, how it does that in a moment. What really influences the ambiguity is going to be the quality of this predictor and the type of nonconformity score that you defined from it. Okay, so the stronger the predictor is, you're really going to influence the ambiguity. The accuracy is just taken care of by the framework itself. Okay, you could have a horrible predictor and it will still be accurate. It might output highly ambiguous labels. So let's look at some examples before I show you how it uses these nonconformity scores. Let's look at some examples of nonconformity scores. So let's say you're using a nearest neighbor classifier. Right, here's your data. A typical nonconformity score, so if you have an input X, and you have to consider each of the possible labels, the nonconformity score for human would be what's the distance to the closest human. So if you're very close to a human, you're going to be close to 0. So you're going to sort of have a low nonconformity score divided by the distance to the closest non-human. Okay? So that's a fairly intuitive nonconformity score. If this is not a human, then the distance to the closest human might be rather large, and you would have a larger nonconformity score. So that's nearest neighbor. Another example would be random forest. So this is a random forest. It's a bunch of trees. And here are the predictions that these trees give in the random forest. So a natural, pretty basic nonconformity score would be the number of trees not predicting the label that we're considering, right? So how many trees did not predict human divided by the number of trees. And that will be larger when a label doesn't conform as well to the true label. All right? And finally, I'm showing you the random forest and neural networks because we'll use those in our experiments. For a neural network, it could be a big convolutional network. The outputs are usually scores, often between 0 and 1. And one nonconformity measure that's used is the max output for the node that's not human, in this case, if you're considering the human label, divided by the output for human. Okay? So these are just fairly natural things, and you could play around with different nonconformity measures, and it would not influence the correctness or accuracy of the conformal predictor, but it could influence the efficiency. Right? But these are the ones that we'll be using. So given a nonconformity score and your favorite predictor, how do we actually do the conformal prediction? We're going to use a framework called inductive conformal prediction. The original work was in a transductive setting, but it's just computationally implausible because you have to retrain your model for every test example. So that's obviously not possible if you're using a convolutional neural network on images. So what we do is we have some calibration data that we're going to hold out. And from that, you can basically get a histogram of nonconformity scores. Okay? And basically out here, these are this is sort of the tail of the nonconformity score part of the curve. And if we get a particular instance, we can ask, well, what's the nonconformity score for animal, hybrid here, that's one of the classes, and human, right? And they land at different points on this histogram, and we can just compute essentially a p-value, right? So you're basically asking the question, for a 95% guarantee, or at least 5% of the calibration scores weirder than the example, than this example with this label, right? So for animal, there's a large percentage of things that are weirder than this particular nonconformity score, and so we would consider keeping animal in the set, right? And we would rule out human because it's sort of at the tail here, right? There's less than 5%, we'll say. So essentially, we're just doing p-value. It's just a p-value, and you're ruling out labels that basically fail a hypothesis test, right? So that's conformal prediction. Fairly basic idea, but you can actually get some guarantees under the assumptions of exchangeability and some basic assumptions about the nonconformity score. All right? So when it was kind of a compelling framework for quantifying uncertainty, but there were really very few experimental evaluations, and especially they rarely looked at ambiguity other than did the system output a single label or more than one label. Not many data sets were used. Most of the experiments were with nearest neighbor, which we found doesn't work very well. We have much better classifiers than the nearest neighbor. And so we just started doing a little empirical evaluation. I'll give you a glimpse of that today with better classifiers than nearest neighbor, random forest for non-image data, and then convolutional networks for images or more perceptual data. All right. And we're also interested in what happens when you take a conformal predictor to an open world. So we'll be looking at that well. So we'll be looking at both closed world and open world performance. And now I'm going to go through these relatively quickly. There's nothing terribly surprising. But if we look at random forest results, we picked out some UCI data sets, and these vary in different ways. We won't get into details here. But this is what a learning curve looks like. So the number of training examples, and over here we have accuracy. So this is number of training examples versus accuracy. We're using a 95% guarantee, and you see early on it's not actually hitting the guarantee. And my hypothesis here is that the theory is based on some basic assumptions, and those assumptions are more clearly violated. There's a higher chance that they're sort of not in the data set for small sample sizes. As you get larger sample sizes, that sort of washes out. But generally, we find that with enough examples, you will hit the guarantee, and that's sort of, these are p-values, so it's not too surprising. And also, we generally find that for these data sets at least, you get zero ambiguity with enough training examples. Early on, you have quite a bit of ambiguity, but remember, zero ambiguity basically means that it's predicting one label confidently. And I've got this green curve here and a blue curve. The blue curve is just showing, remember, the predictor can be wrong 5% of the time. So the green curve is the examples where it's wrong. What's the ambiguity when it's wrong? And here you see that it's a little more ambiguous when it's wrong, but really it gets pretty confident when it's wrong as well. So here you couldn't tell the difference between when it's wrong or right. Just showing you one more. This is more extreme. It just goes to zero ambiguity very quickly. And the other data sets are qualitatively similar. So basically, these learning curves, we've never seen learning curve analysis or empirical evaluations for this. I think it motivates trying to study a little of the finite sample complexity of conformal prediction to understand why these converge so quickly. We also looked at, varying the accuracy constraint, and how does that influence the ambiguity, right? You'd think that if you're going to have a more stringent accuracy constraint, I want 99% accuracy, the ambiguity would probably have to increase. And we see that for one data set here, that's actually the case. So the ambiguity goes up a lot when you increase accuracy. For this one, the predictor just sort of nails it, I guess. And we see that you have zero ambiguity even for high accuracies. Similar. You see a little increase in ambiguity for these data sets. So we're also interested in what would a convolutional neural network do. These are very popular now, of course, state of the art in computer vision, and we're looking at one of the smaller data sets, CIFAR-10. There's a big network that people have trained for this that we're using as the predictor. So we didn't have the resources to retrain this network to produce learning curves. So there are only 10 classes in this data set, but we thought it was a good starting point. So here we were just curious. Well, what would a conformal predictor do with a network? Is it going to have some ambiguity or not? And we see that basically we're varying the number of calibration examples, right? This is what the conformal predictor's p-value is based on. We're not retraining the network for these learning curves. The results would look different if you were, but we wouldn't have been able to produce those in time. But basically we see that the network is very, very confident. The ambiguity is low for all these cases. When you increase the accuracy constraint, you see that the network does become a little more ambiguous. So there is ambiguity once you really ratchet up the accuracy constraint. So there's room potentially to improve. It's interesting to consider how would you train a neural network if you were training it to be a good conformal, to work well with a conformal predictor, right, to minimize ambiguity. Would you be able to do better with a slightly different loss function, for example? So basically, there's nothing surprising in the closed world results. We see that the conformal predictor basically behaves ideally, and you're generally producing zero ambiguity. So when we open the world up to new objects, so a monster might come in. We don't have a current label for monster. That's outside of our closed world, and so what response would we expect a conformal predictor to give for an object that's not in our current model? I mean, what would you want a conformal predictor to give? Any ideas?
Empty set.
The empty set, exactly. Yeah. So smart audience here. So the only really reasonable thing for a conformal predictor to do is to return the empty set. Now, the theory of conformal prediction does not apply at all to the open world setting, but we were still curious about what conformal predictors would do, because it actually is reasonable to expect that maybe these systems will output the empty set in a lot of these cases. So what we did is we set up some open world experiments. And so for the random forest experiments with the UCI data sets, we basically held out a label or two and trained the system on the remaining labels, right? So that held out label is effectively a new type of entity that we can then give to the system and see how it behaves, right? And for the convolutional network, I'll show you the images that we fed it. We just fed it images that had nothing to do with a CFAR 10 data set to see what it would do. So for the random forest, what I'm showing you here is ambiguity, but I'm only showing you the ambiguity averaged over the novel class. Okay, so this is basically how confident the predictor is in outputting a label for the novel class that it should not be confident about, right? It's predicting one of the labels it knows about, but it should not. It should be outputting the empty set. We see that basically it's very, very confident about a single label. So most of the time it's outputting a single label from its set, and it's not outputting the empty set. It's not seeming to be confused by having more ambiguity. So that's what we see there. This data set was, now one thing I didn't point out, negative ambiguity basically means it's outputting the empty set, if you go back and look at the equation. And here, for this one data set at least, random forest knows what it knows. And so for these novel classes, it's outputting the empty set most of the time, right? And but for the other data sets, basically it's usually outputting a single label, and so it does not know what it knows. It's confident in that single label. We would have no idea that this new object was sort of in town, right? So that was random forest. Yes.
I must have missed something. So my intuition is that you're building up a set that is going to have the right thing in it, hopefully. Mm-hmm. And so the less certain you are, the bigger the set should be. Mm-hmm. So shouldn't it be everything?
Well, so you're building this setup, and you're going to put something in it if you can't sort of confidently rule out that it should be out of the set.
Oh, because
Right.
it's just
Yeah.
it's not looking at everything. It's just looking at everything one at a time. All at once.
Well, you could think of it like that, the different labels. And so you would like it to confidently rule out that all of the labels I know about should not be in the set. The theory says nothing about this. This is just our investigation into what happens when you use sort of state-of-the-art predictors and conformal prediction. Yeah, so is that clear?
Yeah, thanks.
All right.
How is this different from the previous slide?
This one here? These are just different data sets. Yeah, so, but qualitatively...
Topography, I thought, was on the previous slide. And
Oh, I probably just mislabeled it or something. Yeah, so yeah, that must have been that was Iris. Yeah, that was the Iris data set here. Yep. So for the convolutional network, remember this was trained on. I'll show you the types of images. This was trained on these images here, right? Sort of natural images of these 10 classes. What we did is we found a bunch of sprites, and we some game NetHack, and it was just convenient that they happened to have the same image dimensions and everything. So we just said, well, let's go with those. So those clearly have little to do in most cases with the data set that it was trained on. And so what we find here is that the convolutional neural network is, again, usually confident about a single label that it knows about. So it's seeing a sprite and it's saying it's a horse or something. And it's not giving us the empty set. It's not reflecting that it's uncertain in any way. We'd have no way of knowing that we're seeing a sprite as opposed to a horse. So that was our experiment with a convolutional neural network, which we found interesting. I think this has a lot to do. There's probably ways to improve this to some degree, but these networks have a softmax function at the final layer, and they're really trying to amplify something that a label that they know about. That's what the softmax is roughly doing. So, in all but one case, there was practically no abstention, right? It was never outputting the empty set, except in one data set where it was able to do that. It's usually confident about a single label, but the theory doesn't apply here, so we can't really complain that conformal prediction is not behaving as we would like it to. But there was sort of reason to believe that maybe it would have. And it appears that standard conformal prediction on its own isn't going to be sufficient for open worlds, right? And so one thing that you might do is you could say, well, maybe we can have new ways of training predictors that will work better with conformal prediction in open worlds. So you can imagine getting predictors that tend to appear more confused when a new object comes in, right? That's what you would like. The neural network output layer would sort of be flat when a new object comes in. And effectively what you'd be doing is you'd be trying to train it to be an anomaly detector of some sort. So that's one way to go at it. And we've got some ideas of how you might try to do that. Another way, and this is another thing that we're going to be exploring, using anomaly detection as sort of a first stage of this whole process. So when something's detected to be an anomaly, well, you've got an anomaly handler, which that's very problem dependent. Otherwise, you're going to go through your normal process. And so the anomaly detector is really going to look at sort of the distribution of the data. Or a lot of times these predictors are just trying to discriminate, and they sort of ignore the fact that there's a really weird aspect to this input because it didn't need it for discrimination. There's some issues here, and this is what we'll be working on. How do you select the threshold in a rational way? And can you provide any sort of guarantees in an open world? Right. So that's where we're going with this. And when we think about explainability, basically, there's a lot of things to explain in this system. Like we haven't talked about doing any more sophisticated explanations of the output, right? If the predictor outputs a set as opposed to a singleton, it's interesting to consider, well, what would an explanation for why it's outputting more than one thing be? What would an explanation be in that context? We haven't studied that yet, but that's something we're interested in. But the other component of this system is the anomaly detector. We'd like to explain, well, if an anomaly detector is saying this thing's anomalous, why is it anomalous? That's a question that we're going to talk about now. So I'm going to go through right. So how much more time do we have?
Right. Well, the next thing after this,
I know people are hungry.
Lunch.
Yes, I don't want to keep people too long.
We started at 12:10. It's now 12:48.
Okay. So I'll try to go for 10 minutes, and we'll be able to eat lunch. So anomaly detection, hopefully a lot of you are familiar with the concept, but these red dots are anomalies. And there's lots of ways to try to define anomalies. We generally think of anomalies as they're generated by a different process from the normal points. And that's not a very concrete definition, but this case study that we're looking at, an anomaly is basically a threat. This was a security application. So a true anomaly is something that a human would look at and say, this is actually a threat. So you've got behavioral data of people in a system, for example, and you want to know, is this person a threat or not? And most anomaly detectors, instead of actually, working with a semantic notion of anomaly, they're looking at statistical outliers. So they're trying to compute statistical outliers. And we're going to consider in this talk density-based anomaly detectors, which this is your data. It will fit a density model to it. We use ensembles of mixture models, Gaussian mixture models. And then you can look at the points with low density values, right? And you would call those anomalies. Now, and if you had an analyst that's going to look at these anomalies, you would just order them by the density values. But of course, not all statistical outliers are true anomalies, and this is just the difference between statistics and semantics, right? So some of these are things that analysts might care about, a true anomaly, and some are just rare normal things, right? So if we, I think to try to understand why we might want explanations, it's worth thinking about this particular case study where our data corresponds to sort of a security application, and some data points are threats and some are not threats, and we want to find the threats. That's the whole point of this this case study. And so you can apply an anomaly detector. You're hoping that it will return all the threats. But it's not. It's going to, here's some missed threats when it outputs the what it thinks are non-outliers. But you have outliers here, and it contains threats and false positives. These are we're going to call type 1 missed threats, and the only way to really improve these this miss rate is by improving the anomaly detector. So after the anomaly detector, you give whatever the anomaly detector says is suspicious to a human analyst. And the human analyst will mark some of them as alarms and feed them to whoever they feed alarms to. So they're going to look at the data, and some of those threats they're going to get, and they might have some false positives as well. But the human analyst might also miss threats too. For example, we say this person looks suspicious. There's a huge database of information about this person. They may not have come across a suspicious aspect. And so we're interested in reducing the missed threats of type 2. And the way we want to do this is by giving explanations to the analysts of why the system thought a particular point was anomalous, to kind of narrow down the data that the analyst has to look at. And this brings up the question of what is an explanation? So what is going to be an explanation? And we'd like that to be tied to sort of thinking about the application. An analyst is going to use this explanation to try to quickly identify whether something's a threat or a non-threat, right? And so the type of explanation we're going to give is something called a sequential feature explanation. The explanation is basically going to be an ordering of the features. You could say it's also an ordering of views of a database, perhaps, where what's going to happen is the analyst is going to first start with the first feature in the ordering and look at it and say, well, do I think this person is suspicious or a threat based on that feature? And if they can't make a determination, we'll show them the next feature. So they'll be able to look at the 2 bits of information. And so we're going to grow this information over time until the analyst can determine that this individual is a threat, or they just run out of time, basically. And then the individual would be termed not a threat. Right? So that's the protocol, and it's very, the type of explanation was motivated by our application goal. And I think that's a general theme when it comes to transparency, because there's many ways you could make a system transparent, but why are you doing it? You have to tie those things together. This is just showing you the analyst's belief in, so we show it the first feature. The analyst is still pretty sure it's a normal data point. We show it the second feature, it's looking at 2 features, and then you show more and more information, and eventually the analyst, the probability that they think it's normal drops low enough, and then this is where you'd have the alarm, right? So if you think of the work of the analyst, how do we evaluate whether an explanation is good or bad? We'd like explanations to reduce the workload of the analyst, which means that the analyst should only have to look at the smallest number of features possible, right? So we'd like to minimize the number of features the analyst has to look at in order to make a determination that a threat is a threat in this case. And we call this the minimum feature prefix, and that's what we want to minimize. So there's a lot to this. I'm not going to go into detail, but basically we have some methods that compute sequential feature explanations. So I'm going to go to a part of the talk that I think might be more relevant. So these sequential feature explanations, I'll just show you one of the methods. So in general, this is a hard problem. We have a branch and bound algorithm with nice pruning rules. But generally, we find that this method works as well as the optimal method as well, and it's a lot faster. Branch and bound can take a long time. So just to give you some insight, we're basically going to pretend that the analyst is thinking according to our density function that we've learned over the data. So their notion of normality is like ours. And so what we're going to do is we're first going to choose the feature that minimizes, this is the density that we've learned over the data, that minimizes the marginal density just looking at one feature. So which feature looks strangest for this example, if you just consider that one feature? And then the second feature will be the one that minimizes this joint marginal density, right? So if I look at 2 features together, which one, if I look at all the features that I could combine with the first one, which one will look most suspicious? So you can keep on doing that, and it's a fairly intuitive, greedy algorithm. We have some other things that were motivated by previous work, but the one I just showed you was the best. So the question now is, how do you evaluate an explanation? And I think this is a question that we struggled with, right? You can look at it and say, hey, that looks good. So anytime you're going to be doing work with explanations, you have to figure out, how am I going to evaluate it? Does it feel good? You'd like a quantitative way when you can get one. So what we're going to do is basically, the problem is we don't have a real analyst, right? So we can't measure how much work they do. And so you have to have some way of doing quantitative evaluations. And so we created synthetic analysts. And this is based on some work that we've done in the past, and there's actually a longer journal version of this, on creating anomaly detection benchmarks from standard machine learning data sets. But you can imagine you have a UCI data set. You pick out some classes that correspond, that you're going to call normal, some classes that you call anomaly classes. And this gives you an anomaly detection benchmark, and you can vary certain properties of it. Now, we could learn in analysts using supervised learning that the analyst will learn the properties that distinguish these anomaly points from normal points. And we can use this as a simulated analyst. So we can sort of simulate the probability that the analyst thinks something is normal given an example, right? So now we've got our simulated analyst, we can do experiments. We can measure the amount of work the analyst would have to do to identify threats. So that's all I'll say about that. And we have some, if you look at producing random explanations, this is what you get. This is averaged. This is a bunch of data sets. But what this means here is that if you give random explanations, the simulated analyst would need to look at roughly 3.5 features to determine that a threat is a threat. Okay? And this is more. We produced optimal explanations, and you see there's a gap between random and optimal. And I'm going to jump to the last bar here. This is what I showed you. This is our best method generally. And we're generally closer to optimal than random there. So we won't go into the distinctions between these methods now. But there is quite a gap between the optimal and our best method in some cases. One thing that, I'll skip through this. But one thing that was interesting, a standard data set in anomaly detection, this is a KDD cup, it's a security data set. We can see that the explanations we produce this kind of shows you the simplicity of that data set and why maybe you shouldn't use it for anomaly detection work. But our best method is able to produce basically explanations that are generally one feature long and can be confidently classified as a threat. So there's usually one feature in any of these examples that sort of indicates that these are threats. So there's kind of a comment on the data set as well. So we'll just say that all the methods basically beat random, and we have one method that we like the best. You can look at the paper if you're interested in that, and basically. I think we're going to continue to do this, do some work as we go ahead. But I think the main points are we had to think hard about what is an explanation. Right? There's many choices that we could have made, and that required us to think about the application that you were using the explanations for. Right? So that was the first point. Whenever you're dealing with transparency or explanations, and then we had to deal with the issue of how do you evaluate your explanation algorithm. And that's very tricky. You'll get papers rejected because people want you to use domain experts to run your algorithms, but you can't get any sort of quantitative results doing that. So the approach that we took was, figure out how to get some sort of plausible simulated analysts, in this case, to sort of feed our explanations to. But you need to figure that out for other applications as well. And I think that's one of the major challenges in doing work on transparency and explanations, I think, evaluation. So with that, I will stop, and it's almost exactly lunchtime. Yeah. Mm-hmm.
So let's take a couple of questions if you want to take 3 or 4.
Sure. Yeah. Any questions? Yes.
So in the thing about conformal prediction, where you're looking at the current method like softmax outputs and then trying to use that to detect whether the object is in a category that's not in the training set.
All right.
Seems like the softmax sort of has the closed world assumption kind of baked into it.
Exactly.
But it seems like it would be easy to sort of stochastically train train with an open world assumption where you just drop some of the labels and replace with like 0, and then see if you can get reasonable results.
Yeah, so this is sort of one of the directions that you could explore. How do you train a neural network or any other model to have better properties in open worlds? And effectively, you're trying to train it to be confused when it should be confused. And that requires, there's a lot of things that go into that, right? So you have to give it some data, maybe that you want to train it on, where it should be confused. That may bias it, so is that actually going to be reflective of the real open world or not? But doing things like that could definitely, that's definitely one direction that we're thinking about. It also seems that ensembles are one way to go about this as well. If you have many models, you would hope that they would be, that they wouldn't be consistent on things from the open world. With random forest, that happened in one data set, but the other data sets, that wasn't the case. But there might be ways of training these ensembles so they have that property. Yeah, so that's a very good point.
And there is a lot of work now in this open category, open vocabulary area. So in computer vision, there is a couple of papers. And there's been some work also in Jihua Zhou's lab in Nanjing. They had a paper, ICML last year, maybe 2 years ago, saying, suppose I have access to a bunch of unsupervised, unlabeled data. I can figure out, between my classes that I have labeled data for, what parts of the space are populated by other stuff. And I should maybe, because the classic discriminative classifier is a partition of the world into K classes, right? And so what he does is discover, there's empty space out here that is not empty. I mean, my classifier thinks it's empty, but it's not empty. So let me pull back my decision boundaries and create empty space so that I know there's stuff out there that I haven't seen. But one question is, what statistical assumptions are you entitled to make about stuff you haven't seen yet? Like, are all those things also IID samples from some distribution, which is kind of what the assumption he's making? Or is it maybe that there's an adversary out there, in which case you don't really make that assumption? So.
Yeah. So any other questions before lunch? Yes.
Yeah, sorry. I also have a question about this case. And you have these conformal predictors that are trying to predict things in open worlds, and the output you want is for them, he said, if it has something that it just doesn't recognize. But if it does have this constraint of that's got to be right 95% of the time, and if right just means containing the
the true label. Yeah.
Could it just be that this constraint is what's causing it to throw in things, and actually you need to fiddle around with this?
Yeah. So the conformal predictor framework does assume a closed world, right? So there's nothing about the theory that suggests it should meet any of the accuracy guarantees in an open world.
Yeah.
There's some intuition that maybe it would, just because of the way it works. It's doing hypotheses tests. Is this a label is this a feasible label for this example? And you would hope it could reject those, but it doesn't. And I think largely it's because these are discriminative systems. They sort of hone in on just the things that you need to look at to discriminate. And they ignore the fact that, maybe this object is purple, and that wasn't useful for discrimination, but the color would be useful for recognizing something that's completely different. And that's why we feel that anomaly detection as a preprocessor is potentially the right way to go, because anomaly detection, it will look at sort of all of the properties. That's certainly there's certainly a lot of things to think about there to get that to work. All right.
So let's thank Professor Fern again.